Right, the next theorem, circuit theorem, is Norton's theorem. It's very similar to Thevenin's theorem. The only thing different is, instead of having a voltage of open loop circuit in series with an internal resistor, now in this case you have an equivalent Norton's theorem, Norton's circuit, which is basically a current supply instead of a voltage supply in parallel with an internal resistance which is connected to your load. So in this case, again, the principle is almost similar, very similar, same. To find the internal resistance is absolutely the same. So you take the load out, and from these 2 points, from that point of view, you look at the system and see how much the internal resistance is without the sources of supply, obviously. So you take the load out, you take the batteries out, short circuit where the batteries were, and look at it from that point of view where the load was connected, and calculate or measure the internal resistance. The same as Thevenin's theorem, no difference. So that will be your Ri, but you draw the equivalent Norton's theorem this way. So Ri will be in parallel with a current supply, which we have to find out what that is and how much that is. Now this current supply is current of the short circuit. That's why we name it ISC, short circuit. To find that one, we have to either again take the load out, put a short circuit here with an ammeter connected here, and measure it practically, or take it out, put a short circuit here, short circuit these 2 points, and measure how much current is going through, or calculate how much current is going through that short circuit path. And then that will be your current of the ISC, or short circuit current for this circuit, for this system. If we have a look at an example, if you have a look at this example, again the same example. Well, in this case, it's similar to that example. It's just got one battery instead of 2 batteries. So you have one battery here, one resistor there, one resistor here, and the resistor of the load connected to it. And now you want to find the equivalent Norton's circuit, which, like I said, it will always look like this with different values, obviously. So the first thing you do, you take the load out, take the battery or batteries out, and short circuit where the batteries were, and then you end up with this circuit to find the internal resistance. So you look at it from the load point of view, where the load was connected to begin with, and calculate how much resistance is there. In this case, you have 2 resistors in parallel, so you just use the formula 1 over 0.2 plus 1 over 0.3. Calculated, it will be 0.12 ohms, or you can just use product over some formula, which is this, and you get the same value, 0.12 ohms, whichever method is suitable or convenient for you. You found the Ri, you just draw the equivalent Thevenin's circuit. So you just draw Norton's equivalent circuit and put that value instead of Ri here. So Ri is 0.12 ohms, and RL, we know how much it is, the load resistance is given, and then we need to find the current, how much short circuit current we have, or current supply. To find that one, we said again, we take the load out, short circuit that path, and calculate how much current is going through this. Looking at this circuit, when you short circuit that area, that path where the load was connected, this has actually short circuited another resistor here. So this is basically eliminated. It doesn't do anything. All the current is going through this path. Remember, current takes the easiest path from positive to negative or negative to positive, whichever you consider it. So now, basically, you ignore this middle resistor, and you have 10 volts over 0.2 ohms, and that will give you the current of the short circuit. ISC equals 10 over 0.2, and that's 50 amps. So that 50 amp goes here in this Norton's equivalent circuit. Now you have a full equivalent circuit with all the values. You can calculate it. Then to find the I that goes through the load, that's easy. You just use that formula. I taught you this formula before, how to find the current in one branch when you have the total current coming and you have two branches or two resistors in parallel. So it's current, the total current times this resistor divided by the sum of those two resistors, which will give you this current. If you haven't watched that video about finding the current in two branches of a circuit with two resistors in parallel, when you have the total current and two resistors, you want to find the current, you can watch that, and that will give you this formula. That will show you where this formula comes from. But again, you don't have to stick to this formula. You can find your own way to find this current. You can find just using Ohm's law and Kirchhoff's laws to find the current here. Right, again, I have more questions here for you to go through for your own practice. But before that, I just say that there is a way to convert from Thevenin's circuit to Norton's circuit. So if you have been given a Thevenin's equivalent circuit, or you have already found it and you want to find the Norton's equivalent circuit, it's very easy. You've already got Ri, so Ri stays the same. This is your equivalent Thevenin, and this is your equivalent Norton. So Ri will stay the same. To find the I short circuit is voltage of the open circuit over Ri, because we short circuit this path, and once you short circuit it, this voltage over this resistor will give you this current, and that will go there. And you can see you can go back this way as well, from this circuit to that circuit, using the same equations. You just transpose for VOC, which is Ri times I short circuit. So if you had the I short circuit, you times it by this resistor, internal resistance, you find the voltage of the open circuit. So you can convert from one to the other. Examples for Norton's theorem. We want you to convert the Thevenin circuits shown below to a Norton circuit and vice versa. Okay, and that's it for me for this session. See you again with another lesson in electrical and electronic principles. Goodbye.